Hello, welcome to Yebo Tutor. Good afternoon. Are you there? Are you around? Is there someone who's with us today? I hope that everything is working out on your side in your grade 11 studies. So let me just see if there's someone around Yebo who is also attending. Are you here on Yebo? Are you also attending this set of questions? Right. So last week we introduced our chemistry and we were discussing a few questions. So now we just want to finish off those multiple choice questions. And my hope is that when you come for your extra work, right? When you come for your extra work and you get out your calculations and so forth, it is my hope that we get to ask the necessary questions. We get to ask the relevant questions. That's important for us because at this stage, what we want to understand is what's actually happening in order for us to get a grasp of the chem. So we are working out chemistry paper 2, 2015, and then we will go to the next paper for the next year and so forth and continue with those calculations. Last week, we looked at the definition of bases according to the Arrhenius theory, and we came up with the definition according to the spontaneous splitting of water. Now, we also built a small atom and we played around with building an atom and seeing. So there is a word that I asked from you. So let me just check to see if we did some work. There's a word that I asked from you, if you still remember. Do you now have that word? There's a word that I asked from you. That word is basically describing what is taking place, or it defines some atom, such as that other nitrogen that we had. So that nitrogen is this one. So it's a comparison of this atom to the nitrogen that we see in our periodic table. The question that I asked is, what is the definition of this other atom? What is the definition of this other atom? What type of an atom is it? What is the definition of this other atom? So I'm just hoping to see a comment in the chat so that you can tell us the name of that atom. I think that was one of the pieces of homework. I think there was something else again. I just don't quickly remember. All right, so let's jump on to question 3. Let's jump on to question 1.3. So question 1.3. Which one of the following has the strongest forces between its molecules? Which one of the following has the strongest forces between its molecules? Right. Which one has shows the strongest forces between its molecules? I hope that we still remember the topic on, because we're looking at between molecules, so that's intermolecular forces. Intermolecular forces. So the question now is, if we have that fluorine gas, chlorine gas, bromine gas, and iodine gas, which of these has the strongest forces between its molecules? So how do you determine what are the factors? What are the factors that affect or that determine the strength? Yes, let's say determine. That determine the strength or the magnitude of intermolecular forces. The strength of intermolecular forces. So what are the factors? So we will maybe let's just tabulate this. So we will have a list of the factors, and then we will categorize them, right? We will categorize them, and we will say the first gas there is fluorine gas. First of all, this gas, these answers, do you notice that they are in one group? Do you notice that all these answers are in one group? Which group of chemicals are these? Which group of chemicals do we see there? These fluorine, iodine, bromine, chlorine, they are all in one group. So which group do they belong to? Which group of chemicals or elements on the periodic table do they belong to? Can you please tell me the group? I'm just looking for our periodic table so that we can compare what we see there. So there is this data sheet. Let me just open. If I say open with Chrome, can you see it? Let me see. Let me put it here. There's a calculator somewhere. This one, yes. So let me open it onto this page. Let me open it onto this page. So I'll just copy this and paste it there. Good. So I've got some constants here. I'll just rotate this so we can see it. And I was saying, do you see that these molecules, these gas, the elements that make up these gas molecules are all in one group? Are all in one group. So the question is, what are the factors that affect or that determine the intermolecular forces? What are the factors that determine the intermolecular forces, so that we can compare them down this trend? So that we can compare them down this trend. I wish I could label this. So what I'll just do is to put F2 gas here, and I will say all the way to our last one is I2, all the way to I2. Right, let's go to the factors that affect these molecular intermolecular forces. Factor number one that affects intermolecular forces would be the molecule size. Just the size of the molecule would mean that the bonds that are formed in between separate molecules have a certain magnitude. If the molecule is larger, what happens to those bonds? If the molecule is larger, what happens to those bonds? So let's just check for your intermolecular forces. May you please give me the factor? What happens as the size of the molecules increase? Obvious, in this case, the size is what is increasing, right? So let's just say increasing. So that's the size of the molecule. The size of the molecule is increasing. That's what we're seeing. That's the first factor, right? So I'm just hoping to see one of you giving us the second factor. So what is the second factor that we can pick? The second factor that we can state, and we can say this factor, it affects intermolecular forces, and down this trend or down this group of halogens, then this factor increases or decreases, and then affects the force in this way. What's the next thing? Have you ever thought about this one? Melting point. Have you ever thought about this one? What happens to the melting point down this trend? what happens to the melting point down this trend. So if you want to check, you can even look for melting points of these halogens. So let's just say melting points of, let's say, halogens, right? Down the group. Yes, someone searched for that. Melting point of halogens down the group. Look at that. Look at what's happening to these melting points. Right, so if you have a textbook, please check in the textbook so that you verify these values are from a source or a website called ChemLibreText. So it is important to make sure that you can use a data sheet, right? There must be a data sheet that you use so that you don't just get this, because anyone can write a website. Even I can write a website if I learn how to. Then I put some numbers. So what if I'm wrong, right? So let's also be careful of sources. But what are you seeing in this trend? The melting point is minus 220 for fluorine. For chlorine, it's minus 101. For bromine, it's minus 7.2. For iodine, it's 114 degrees Celsius. Is this melting point increasing or decreasing down this trend? Is this melting point increasing or decreasing down this trend? Minus 220. Then it becomes minus 101. So if we were to put it on a scale, right? If we were to put it on a number line, that would be our number line. Instead of this number line being X or Y, I will put melting temperature. So it's T, let's call it T melting, representing melting temperature. So this is increasing, this is our 0. So this is our negative axis. For fluorine, so let me just try to make a graph, right? Just out of interest. I'll make this graph and it will have steps of, let's say, 50. So this is a step of minus 50, minus 100, minus 150, minus 200, right? And then minus 250. Then up the scale, it has a 50, a 100, a 150, which may not be necessary now. This is in degrees Celsius. So I said this is a 50, 100, 150. Then we have our minus 50, minus 100, minus 150, minus 200, minus 250. This is all in degrees Celsius. So I'm trying to make it small now so that we can try to identify our gases. So if you are here, you tell me, where can I put fluorine on this number line, on the melting point? Where can I mark to show the melting point of fluorine so that I can put its mark? So fluorine is at minus 220. So this is minus 100, sorry, minus 50, minus 100, minus 150, minus 220 could be somewhere there. Then I will put the label F2. Chlorine is at minus 101. It's almost 100 in the negative. So I'll put that and put a label called Cl2. Then I will, okay, let me just put the elements rather. Let me put the elements, right? Because they are written as elements. Let's have the next one. Let's have the next one. Let's have the next one. Rather, let's actually have halogen molecule. Let's have halogen molecules. Molecules. Right. So that the values will make sense. Okay, I'm seeing a lot of options there. Let's see. Down the group, melting point, down the group. Is there someone who wrote these specifically for halogens? Specifically for halogen gases or halogen molecules. Right. These are just configurations, halogen. Okay, so I'm not getting a atomic radius, ionization energy. I'm not getting a specific gas, but in any case, we have two chlorines that are bonded. We have two fluorines that are bonded. So obviously, the trend should be the same. So I will just continue to use these values. Let me just go back to what this is what we had. This is what we had. So let me just blow it up, make it larger so you can see. All right. Okay. This is the best we can get. We want melting temperatures. Okay, there we go. Melting point, so minus 100 for chlorine, and then minus 7.2 for bromine. So that would be somewhere here. So that would be our Br. Iodine 114. 114 would be somewhere there, and it's a positive value. That would be iodine. Then we've got a 300 for astatine. So when you look at these numbers, are they increasing or decreasing? This is the trend. This is the trend according to the question. FClBr. So FClBr all the way to iodine. Do you notice we are actually increasing in temperature? So therefore, we can also say melting point here is increasing. The melting point here is also increasing. So if the melting point is also increasing, you can imagine that obviously the bonds are very strong, because it means for chlorine we need very little heat at a temperature of just minus 220 degrees Celsius. But we'll have to increase that temperature in order to start breaking the bonds in chlorine. We will also need to increase it again for bromine, increase it for iodine. So therefore, the intermolecular forces in this case, they are strongest in what? In that iodine at the bottom there. So our answer for this case would then become D. Answer would become D. Right. Let's have questions. On this part. So this is our question number 1.3. I just want to circulate the answer so that you can also see it clearly on your side. So that's it. That's our value. Right. So those are the bonds. The next one it has to do with which one of the following has a tetrahedral shape. So how do we determine the shape of a molecule or a compound? How do we determine the shape of a molecule or a compound? So 1.4 is for us to find the geometry. So the shape or the geometry of a molecule. Molecular geometry. So how do we determine the geometry of a molecule? How do we find the geometry of this molecule? How can we find the geometry of this molecule? So there are many steps that you can use to try and figure out the geometry of a molecule. For you to figure out the geometry of a molecule, first of all, I think the last stages of the geometry selection are the stages which lead you to look for certain things, right? So what are the stages, or what are the inputs, or what are the necessary factors that we check for us to determine the geometry of a molecule? So obviously, for the geometry of a molecule, these are the factors to consider to determine the geometry of a molecule. So number one, we need the what? The number of bonding pair electrons. Number of bonding electron pairs. Electron pairs. When we have a bond, for instance, for HO3, how many electron pairs are used for bonding? So we'll look at the central atom, obviously, and find out the number of electron pairs that are used for what? For bonding. So you're looking at the central atom. So once you have those, then you just look at the number of lone pairs. Number of lone pairs. You compare the number of the bonding electrons, the pairs, and the number of lone pairs. So then you will determine a geometry. So let's just write that table down so that we recall these numbers. So let's write that table down so that we can recall these numbers. Rather, we can even pull it out from your text, isn't it? I think we can even pull it out from your textbook so that you can see where we're getting the criteria. Now, where is this textbook? I will just look for a simple textbook like the Siyavula textbooks. So you can just check on your Siyavula textbooks so that you can get to see numbers. So I will choose to open this here. Right, there we are. So that's our textbook, and all we want to find are the criteria, isn't it? Are the criteria for finding those lone pairs. So let's just scroll. The chapter is on what? It's on molecules and bonding. So let's just see if there's someone here. Are you here? If you're here, may you please immediately put the chat. So you can put to the chat and tell us the number of lone pairs in each of these molecules. Number of bonding electrons in each of these molecules. Then we can easily determine the lone pairs. Okay, so let's see how we can find the geometry. Let's just look for that chapter. Right, so while I'm doing that, I will just wait for your responses. While I'm doing that, I'll just wait for your responses so that we can see. Right, we've got some bonding here. Okay, so we've got some bonding, chemical bonds. That's the chapter. Right, so I need a table for the geometries. So I've just pulled out this table. So which means you can just revise this table. That is your guide. So that's the table that can give you a calculation method to find the shape of the molecules. Okay, so let's now draw or tabulate our molecules. Find the number of bonding electron pairs. Find the number of lone pairs, and then the geometry will be determined from there. Okay, in terms of the formula, someone may want to immediately try and use these formulae, so you can also do that. However, if you want to see how to get to that, then you can also make use of the basic principles. So I will just write each molecule and see its bonding structure, determine its number of electron pairs, determine its number of lone pairs, and then figure out the geometry. So let's have the molecule. So this is our molecule. Then this is its structure. This is its number of electron pairs. So let's call it number bonding pairs. Then number lone pairs. let's actually bring this here. Let's bring this there, bring this there, and then number of lone electron pairs. And the last one is the geometry. So that's our table. So with a table, you can get to see how you categorize these properties. You can get to see how you categorize these properties. Okay, so I'm at a page break. Maybe let me just take this downstairs. Let me take this downstairs. All right, I just need this. Bring it here. Yeah, somewhere there. Okay. So in this table, we will just have the first molecule. It's our H3O hydronium molecule. In the second part, we will have the ammonium molecule, the ammonium compound. The third, we will have a carbon dioxide molecule. The last, we will have an aluminium chloride, a trichloride molecule. So this is the structure. So let's just work it out like that. That is the structure. That is the bonding pairs. That's the lone pairs. The question is how you get to these. It's very easy for one to start by figuring out the answer quick, right? The question is, how do you get to it? If the question says, show all steps, then how would you write it? If the question is in this section, right? If it's in this section, section B, right? And it says, show all steps, and it writes here, show all steps. The question is, how do you do it? So that's what we're trying to work out here. Good. So your structure of the hydronium molecule. Obviously, your hydronium is a what? Is a hydrogen plus a what? An oxygen. So you look at the Lewis structure. The Lewis structure of your hydrogen, hydrogen would only have one electron in its outermost shell. I'm not yet looking at that, so we will look at that when we are making up the complete bond. Your oxygen obviously has what? It's in group 6, so it has 6 electrons in the outermost shell. So let's combine them now. So obviously here we have our oxygen as the central atom. That's our oxygen. And it will have the 6 electrons in its outermost shell, the valency electrons. So our hydrogen is there, our second hydrogen is there, our third hydrogen is there. But obviously the third hydrogen is the ion. So it has no electrons in its what? In its outermost shell. Therefore, we should have a what? We should have a dating bond. So we should have a dating bond there with oxygen. Then here we will have this hydrogen contribute its electron. We will have the other hydrogen contribute its electron. So how many do we need to complete the number of electrons that oxygen actually has? Oxygen has 2 more, so that we have 6 electrons for oxygen and 1 electron each for the hydrogens, and we have this ion that does not contribute any electrons to this. So let me just bring it closer so that it's not too far from the diagram. There we have it. So that's our diagram for the what? For the hydronium ion, and that is its structure. Right, so if we have the hydronium like that, let's now figure out how many bonding electron pairs do we have. Let me just say electron is like this. Let me say electron is like that. Just putting a shortcut. Right, so how many bonding electron pairs do we have in this structure? How many bonding electron pairs do we have in the hydronium structure? These are bonding, obviously. They are bonding what? Oxygen to the hydrogen ion. These are bonding the oxygen to the bottom hydrogen atom. These are bonding the oxygen to the left side hydrogen atom. So the actual bonding electron pairs that we have, 1, 2, 3 bonding pairs. So we can say 3 bonding pairs. How about the number of lone pairs? How many lone pairs do we have? In this case, we have 1 lone pair there, so we can write our 1 lone pair. So you can also find out from your teachers if our dating bond there will actually be categorized as a lone pair. Then your geometry, if you look up number of bonding pairs, so let's now look up in our table. Number of bonding pairs, we said 3 bonding pairs. So we have these 2 cases. It's either this or that row. Number of lone pairs, we have 0 lone pairs there, but we have 1 lone pair. So we are looking at a trigonal pyramidal shape. Trigonal pyramidal shape. So this one is not what we're looking for because they are looking for a tetrahedral shape. So this one is trigonal pyramid. Trigonal pyramid. How does it actually look like? How does this trigonal pyramid look like? I hope we have an idea of how these look like. Let's move to the next one. Ammonium. Let's move to the next one. Ammonium. So I will just separate this like this so that we don't confuse the Lewis structure of the separate atoms and the Lewis structure of the bond that we created. So I will do the same here and say we should have hydrogen with that one, and we add, these are 4 hydrogens, this was 3 of them. Then we should have a what? We should have a nitrogen. So what is the Lewis structure of our nitrogen? In which group is it? In which group is nitrogen? So you can just come and check in your periodic table. Nitrogen falls in group 5. So it has 5 electrons in the outermost shell. So there we go, the first 2, the last 3. So those are our electrons in the outermost shell. 5 electrons in the outermost shell. Let's now draw the bonded structure. So that's our nitrogen, obviously in the center because it's just 1 nitrogen. And we now have 4 hydrogens. 1 is an ion because it's what? It's positively charged. So let's see how we can draw this. Let's see how we can draw this. I would like to put the ion on top. So I'd like to pull this, right, a little lower. Make this diagram slightly larger. And then maybe make this N a little smaller so that my diagram can fit in this small space. So our first hydrogen, let's say it's at the top here. I'll make that the ion. Immediately, the one at the top, I'll make it the ion. So it will share a dating pair. Then one of the hydrogens on the left will contribute an electron, and then we have one from the nitrogen. The other hydrogen here will contribute an electron, and we have the other from the nitrogen. The other hydrogen here will contribute an electron, and we'll have the other from the nitrogen. Do we still have 5 electrons in the outermost shell of the nitrogen? Yes. 1, 2, 3, 4, 5. So we're still fine. Do we have 1 electron each for the hydrogens? Yes. 1, 1, and 1. Do we still have the ion that will produce a positive charge? Yes. And it's on a dating bond. Okay. So let's now put these into perspective. Let's now put these into perspective. What are we supposed to look for? We're supposed to look for the number of bonding electron pairs. The number of bonding electron pairs. How many electron pairs are bonding here? 1, 2, 3, 4. So these are 4 bonding electron pairs. How many lone pairs do we have? Do we have any lone pairs here? We have a dating bond, but we don't have a lone pair. So we have a 0 number of lone pairs. If we look at our structure, we have, let's look at this one with 4 bonding electrons. We've got the tetrahedral structure for ammonium. So that's tetrahedral. tetrahedral. How does a tetrahedral structure look like? How does a tetrahedral structure look like? So we'll look at that and when we are done. Okay. So let's jump on to the next one. Let's jump on to the next one. The next one is carbon dioxide. Let's also see, because maybe there are two answers here. Carbon dioxide, as usual, we have a carbon and we have two oxygen. So two oxygens. So let's just put the Lewis structures of the separate ones. Jump onto your tables to find out the number of outermost shells for carbon. For carbon, number of outermost shell electrons, rather. Excuse me. So for carbon, that's 4 electrons in the outermost shell. So let's make them 1, 2, 3, 4. For oxygen, as usual, we have 6. 1, 2, 3, 4, 5, 6. So let's draw the bonded structure. Obviously, we have 1 carbon, so it will be in the center. Right, so we have plenty of electrons to use here. So we can actually have 2 electrons from the what? From the carbon to bond with one of the oxygens. So this is how we form the double bond. We can have the other 2 for the carbon to bond with the oxygen. Let's complete the electrons for the oxygens. Oxygen has 6 electrons from this Lewis structure. So we need what? We need 2 more pairs for each. So there goes the first pair, there goes the second pair, there goes the first pair, there goes the second pair. So we're done. So we have a double bond. Double bond. And our system is stable. You see, carbon is happy. It has what? 8 electrons in its outermost shell. So now that we have this structure, again, we look for number of bonding electron pairs. There are 2 pairs on this side, right? There are another 2 pairs on this side. So we will have a what? We will have a total of 4 bonding electron pairs. 4 bonding electron pairs. Number of lone pairs. Do we have any lone pairs? No, we do not have. Right? So we have a case here. We have a case here. Right? Do we call these 4 electron pairs? Do we call these 4 electron pairs? Do we call these 4 electron pairs? So there we should have what? We have 2 bonds. These are just double bonds, right? So we should have 2 bonds. So please just go and check on this one. So we have a pair, bonding pairs on this side, right? And then we have a bonding pair on this side. So just cross-check that one, and then you will have a, what is the shape? We have no lone pairs there. So may someone just go and check for us. Check for us. So that would be linear, right? That would be linear for the carbon dioxide. That would be linear for the carbon dioxide. So the bonding electron pairs, we just have 2 pairs that are bonding. 2 pairs that are bonding. All right, I think that we can check the last one, which is aluminium chloride. Aluminium chloride. So you have your Al there and you have your Cl. So it's 3 of them. Lewis structure. Let's just see if there's someone who's joined us. Let's just see if there's someone who's joined us. If you've joined us, please tell us how you are coming up with these answers and if it is making sense to you. So today we are running on some chemistry and we're looking at bonding, molecular bonding. molecular bonding. Right. So we've done Al. We know we've got 3 electrons in the outermost shell. So I'll just put an X there, and X there, and X there. For chlorine, we have 7. So 1, 2, 3, 4, 5, 6, and a 7th. 1, 2, 3, 4, 5, 6, and a 7th. So the aluminium is obviously the center atom. It will have 3 chlorines. So that would be 1 of the Cls, the 2nd of the Cls, the last of the Cls. This Cl will contribute, the aluminium will contribute, the Cl will contribute, aluminium will contribute, and so on and so forth, right? And so on and so forth. So let's now put the rest of the electrons for the chlorine. We've used only 1, so we're just going to put the rest. 1, 2, 3, 4, 5, 6. The same applies. 1, 2, 3, 4, 5, 6. So there we go. We now have our aluminium chloride in that form. Number of bonding electron pairs. How many electron pairs are bonding? So the number of bonding electron pairs there would be 1, 2, 3. So that's 3 bonding electron pairs. How many lone pairs do we have? We have no lone pairs. So for a 3 bonding electron pair system, we are looking at 3 bonding pairs and 0 lone pairs. This one is a trigonal planar. So that's trigonal planar. Right. So from this exercise, one can tell that our tetrahedral shape is from what? From NH4, right? Our tetrahedral shape is from NH4. So just out of interest, how do these shapes look like? How do these shapes look like? So I just want to see an example of the shape of a molecule. An example of the shape of a molecule. Let me just pull this out for you. Let me pull this out for you so that you can probably relate this to what we actually see with our eyes in terms of geometry. So let's have something there that will demonstrate the structure of these molecules. So that's molecular shapes. You can go online. This is a free site called PHET simulations. If you just look for PHET simulations, they have very exciting demonstrations and animations. Okay, so there are some molecules here. Let's see one which fits what we have. Do we have hydronium? No, we don't. Do we have NH4 plus? No, we don't. Do we have carbon dioxide? Yes, we have carbon dioxide. There we are. So electron geometry and molecular geometry are just showing us that this is our carbon dioxide molecule, right? So the carbon dioxide molecule has these electron pairs. These are what? Our bonding electron pairs. These are bonding, so we just have a double bond. Electron bonding pairs and our individual oxygens here. So look at the symmetry. So this will be a symmetric molecule. In other words, the electrons distribute themselves in such a way that there is the least repulsion amongst the electrons. So that's why these molecules end up having a symmetric shape. So that is the structure of our molecule. Let's just see if we have, so bond angles, the bond angle is 180 if it's going to be necessary elsewhere as you study. Let me just see, we've got some examples here. So we want to build a molecule. So there's some lone pairs that we can choose. We can show some bonding structure. Now for the hydronium, we would need three of the hydrogens, right? And then we would need one lone pair. So 3 bonding pairs and 1 lone pair. So this is what we've done. We've created a model of the hydronium molecule. The hydronium molecule will have a distribution which looks like this. It has the oxygen, right? So that's our center. Sorry, it has the nitrogen. Oops, hydronium is this one. Yeah. So it has the oxygen. Then it has the hydrogens, right? With single bonds. Then it has this what? This lone pair. So it ends up looking like a trigonal pyramid. So this is what is called a tri for 3. It's gonal, it's a polygon, but it's like a pyramid, right? So you can draw the baselines of this pyramid. Then you've got your trigonal pyramid structure. How about a tetrahedral structure? So let me take away this lone pair. Let me take away all these bonds. Let me take away all these bonds and start afresh. So we've got our nitrogen in the center there. We've got 4 hydrogens. So they are made of single bonds. So how many bonding electron pairs? 4. Electron pairs? 4. 1, 2, 3, 4. Can you see how they are distributing? So that the bond angles are equal and there is minimal reaction, minimal repulsion of the electrons. Then, now that we have that, how many lone pairs did we say we have? 0 lone pairs. So that's our tetrahedral. So our molecular shape here is tetrahedral. It's not very clear here, but I hope that you can do it on your own, on your computers. You can actually see it. So let me just check for the previous one. If it told us the molecular shape. So we said it was 3 of the bonding pairs, and then we had a lone pair. Yes. So it told us that it is trigonal pyramidal. The next one was our carbon dioxide. So our carbon dioxide, we saw it earlier, but we can just build it out of interest. So we've got our 2 bonds, and we're done. We don't have any lone pairs. So it becomes linear, right? So it becomes linear. So which means we need to be particular about this geometry. They will stretch in such a way that these molecules, the electrons must repel with the least force. These electrons must not be close to each other, you see. So they repel until they repel the least, right? So that's our molecular shape. Let's look at the last one, aluminium chloride. So it's almost the same as what we had before. It has no lone pairs, so it will be slightly different. So we just have that bond for each, of the chlorines. One bond for each of the chlorines, no lone pairs. So it becomes a trigonal planar. So that's your molecular shapes, and which means from here you can take it and look at any other examples, right? Go into your textbook. If you want to find your molecular shape, just draw your Lewis structure for the individual elements. Then determine the center atom. It's obviously the one which is the lesser number of the atoms. And then you come to the bonding pairs. You look for them by just counting. And you're done. So let's just hope that all is in order for you to get to the next question. Any questions on 1.4? Any questions on 1.4? So our correct answer there for 1.4 is B. Our correct answer there for 1.4 is B. I'll just remove this because I wanted to give an example. So I'll just remove it. Right, let's jump on to question number 1.5. Question number 1.5. Question 1.5. 2 molecules of hydrogen gas at standard temperature and pressure occupy a volume of how much? So these are molecules of hydrogen, molecules at these are of H2 at STP. Molecules of hydrogen at standard temperature and pressure. So what kind of a volume, how large a volume do these molecules occupy? How large a volume do these molecules occupy? So what happens? how do we determine the volume, or what relationship can we make use of to derive some equation for the volume, right? To derive some equation for the volume. So I'm just waiting to get an answer from you, or maybe you're still working it out. What do we see there? How do we get the number so that we can compare? How do we get the number so that we can compare? Right, so the first thing is, this is a gas at standard temperature and pressure. So what happens to real and ideal gases? What happens to real and ideal gases? Real and ideal gases. What happens to real and ideal gases? With hydrogen, if we are at standard temperature and pressure, it will behave like an ideal gas. If we take it to extreme values of the temperature and pressure, that's when it starts to deviate from the ideal gas behavior. So this means in this question, the equation that we will need is the ideal gas law. So that's our PV is equal to nRT. That's our ideal gas law. PV is equal to nRT. Now, we want to find the volume. We want to find the volume. They want us to calculate the volume. How do you calculate this volume? How can you figure out the volume? If you have been given the equation for PV is equal to nRT, how can you calculate the volume? So your volume, if you divide both sides by P, divide both sides by P, divide both sides by P. The P's on the left-hand side will cancel out. The P's on the left-hand side will cancel out. In the end, you have the volume being equal to nRT over P. nRT over P. So, it's time to substitute values now. It's time to substitute values now. What is N representing? N represents the number of moles. N represents the number of moles. This is your universal gas constant. So that one is a constant. How about the temperature? When we are talking standard temperature and pressure, what value is the temperature? What value is the temperature when we talk standard temperature and pressure? And your pressure, standard temperature and pressure, that would be 1 atmosphere, 101.3 kilopascals. 101.3 kilopascals. So you can now substitute all these values. You can now substitute all these values from this equation. So let's substitute away and see what we can get. This is 2 moles. They've given us the number of moles. So that's 2 moles. What is the value of your universal gas constant? What is the value of your universal gas constant? So here, as you can see, your data sheet is very important because you can easily access all these constants. So you're given Avogadro's constant, molar gas constant, which is what we want to use here. So that value is your 8.31 joules per Kelvin per mole multiplied by your 273 kelvins. What are we dividing this by? 101.3 kilopascals. What is kilo? Times 10 to the power of 3 pascals. Now let's just see if the units of measure agree with what we are doing there. Remember, this is in moles, so it would cancel out with per mole. So we now have our 1 over pascals for us to get the value of the units. In fact, we've got joules over pascals. Okay, so you can also do a dimensional analysis and say, if we have joules over pascals, what do we get in the end? So joules are units of measure for what? For energy, right? And we know that energy is the same as the units of measure for work. So this is equal to a force times a distance, right? Then you also have your pascals, which are a pressure. What is pressure? Pressure is force over area. So these are newtons per square meter. So in the end, your newtons cancel out. Meters will multiply square meters so that you get your volume in cubic meters. So the answer that we have written here is in cubic meters. So let's just punch in the values in a calculator so that we can see if this is true. 2 multiplied by 8.31, your universal gas constant, multiplied by your standard temperature. Then you divide everything, so we are dividing everything by 101.3 multiplied by 10 raised to the power of 3. So 10 raised to the power of 3. The answer that we are getting is 0.0447 and so forth cubic meters. Remember what we did here. So this answer is in cubic meters. That is the volume of this gas. So 2 moles of hydrogen would occupy 0.447 and so forth cubic meters. So this value that we have here, as you can see, the values that are given are in dm cubed. So our values are in dm cubed or decimeter cubed. So the question is, how do you compare a decimeter to a meter, right? So 1 cubic meter, we want to compare, okay, 1 decimeter, let's write it as 1 decimeter. 1 decimeter, if you would cube it, you would get 1 dm cubed. So 1 decimeter is the same as 1. A decimeter is 1 times 10 to the minus 1 of a meter. Then you cube that. This would give you 10 to the minus 3 cubic meters. 10 to the minus 3 cubic meters. So we now have a relationship between our decimeter cubed and the cubic meter. So this must mean that if we divide both sides, remember this equation now says 1 dm cubed is equal to 10 to the minus 3 m cubed. If you divide both sides by 10 to the minus 3, divide both sides by 10 to the minus 3, and these will cancel out, you will find that 1 cubic meter is actually equal to 10 to the power of 3 dm cubed. 10 to the power of 3 dm cubed. So now we can put this into our value, since the values for our answers are given in what? In dm cubed. So our volume is therefore equal to 0.447 and so forth. So I'm not yet rounding off. 0.0447. Let me just say 9 and leave it there. These are cubic meters. And we now know that we've got 10 to the power of 3 dm cubed in every cubic meter. We have 10 to the power of 3 dm cubed in every cubic meter. So therefore this is equal to 0.04479 multiplied by 10 to the power of 3 dm cubed multiplied by 10 to the power of 3 dm cubed, because the m cubed cancels out. Okay, so this must mean that we should multiply this value that we got by 1000. So that must be that value times 10 to to the power of 3, so that your answer becomes 44.79 dm cubed. According to the numbers that were given on the screen, the nearest is therefore 44.8 because they rounded off to 1 decimal place. Therefore, your volume is 44.8 dm cubed, and your correct answer is D. Your correct answer is D. Any questions on that? Any questions on that? I trust that you will take this equation and make use of it elsewhere, because what is most important is the principle and how we apply it to a particular situation or setup. Okay, so that's the universal gas equation, which gave us some values. So which means what I'll do is for next meeting, next week, for next meeting, I'll try to move a little faster so that we cover maybe more questions, so that we end up covering more topics. It looks like we still don't have in attendance, so I just hope that for next week I will have someone here to be working with, so that we can see how we can solve the next set. So which means our next question will be question number 1.6. I think this one is more straightforward. It's just which one of the following statements correctly describes the characteristics of an endothermic reaction? The characteristics of an endothermic reaction. So for an endothermic reaction, let's go and figure out the difference between an exothermic and an endothermic reaction, so that when we meet next week, you can tell us which of these is true. Is the delta H positive or negative? Do the products have less or more potential energy than the reactants? More than or less than the reactants? So I will be waiting for your answer for this one. Remember, I still have homework that you need to give me. I gave you some homework. It's a very simple thing. You're just going to look at a nitrogen 14 and a nitrogen 15 and tell me what is nitrogen 15 in relation to the normal or the usual nitrogen. So just maybe in case you are following, maybe let's just clear this question so that next week we start on the next. So which one of the following statements correctly describes the characteristics of an endothermic reaction? Which one of the following statements correctly describes the characteristics of an endothermic reaction? So for an endothermic reaction to take place, what do we need? For an endothermic reaction to take place, what do we need? We need what? We need heat, isn't it? We need to actually, it requires heat for it to take place. So, which means our delta H in this case will be given as a positive value. Our delta H will be given as a positive value. So that's the first case. Our delta H is positive for an endothermic reaction. When we started, we had some reactants. These reactants, let's just call it A plus B formed C plus D. Right? They are in their states, maybe solid, liquid, aqueous, whichever way. So when we had these in our beaker, nothing happened. We just mixed them. Nothing happened. And we waited and waited. Nothing happened. So this reaction will not take place. It needed some heat, right? So when we look at what we call delta H, this is our H final minus H initial. H final minus H initial. That's our change in the heat supply to this process. So remember, here the reactants are at a temperature H initial. The products are now at a temperature H final. what did we do for this to take place? We added some heat. We added some heat. This means H final is actually greater than H initial. The heat energy for the products is actually greater than the heat energy for the reactants. If the case is that, then it means we can now look for the correct answer among these. So delta H is what? Is positive. So this one would qualify. It says then the products have what? Less potential energy than the reactants. No, this one wouldn't work now. This one wouldn't work. Because if the products have less potential energy, then we are in trouble. Because what would have happened then to the heat that we added? What would have happened to the heat that we added? So that first one is not going to work as a correct answer. Second one, delta H is positive, so this one qualifies. The products have more potential energy, right? Products have more potential energy. So this one works for our criteria because if they have more potential energy, it means H final is greater than what? H initial. This is what would make delta H equal to H final minus H initial a positive value. So we can stick to B. Then the third one says delta H is negative. This one is outright out, right? This one is outright out. Our delta H cannot be negative for this reaction because we're actually adding heat into it, right? Then our delta H is negative for the other one, so that doesn't work. So our final answer is B. Our delta H is positive. Delta H is positive, and the products have more potential energy than the reactant. More potential energy than the reactants. So this was an important part for just the definition of the heat process for an endothermic reaction. So I just want to find one last demonstration for this process. I'm looking for one last demonstration for this process. I hope I can find it. If I can find it, you will see it on the screen in a second. You will see it on the screen in a few moments so that we can tell what really happens with these chemical reactions. Right. So I just want to maybe use molecules here in this reaction. I really can't see. I can't see what's happening. So just give me a moment. Give me a moment, please. Okay, I do not have a demonstration for that. Okay. So I just wanted to show you something, but I can't seem to find it here. So which means then this leads you to work on the next question. I hope to have some answers already from you. Which one of the following balanced reactions is a redox reaction? And then during the extraction of gold, we read this one. We are looking for the oxidizing agent. And then the volume of the gas is given by that. If the temperature is doubled and the pressure is halved, what do you do there? And then the last one. So you go and work out questions 1.7 to the last. You go work out questions 1.7 to the last, to question 10. Then bring your questions, right? So you can put them on the chat. There's a chat, a WhatsApp chat, I understand. Then you can also put them onto this YouTube channel when you come to attend. Right. So let's call it a day for this week. I hope that the chemistry is coming up. I hope that we are getting into the excitement of these calculations and solving these problems. So let's get to rest a bit for the weekend and meet again next Friday, same time. So from me, Nyasha and the Yebo Tutor team, we wish you all the best. We wish you all the best. Goodbye.